Good afternoon. My name is Darinel Ortiz Montaño, and today I will be presenting our research in development and characterization of a sustainable biopolymer from sargassum SSP and sawdust for advanced material application. Plastic pollution has become a global environmental crisis, with conventional plastics persisting for centuries and causing significant ecological damage. In parallel, coastal communities face seasonal overgrowth of sargassum, an invasive seaweed that disrupts marine ecosystems and local economies. Similarly, sawdust, a byproduct of wood processing, is often discarded despite being abundant and biodegradable. Our research proposes a solution that integrates these two waste materials into a value-add product, a biodegradable biopolymer. By combining sargassum SSP and sawdust, we aim to create a sustainable alternative to conventional plastics while exploring potential applications in packaging, agriculture, and eco-friendly construction. The objectives of this project are threefold. Development: to produce a biodegradable biopolymer using sargassum SSP and sawdust. Characterization: to evaluate its physical, structural, and thermal properties. Optimization: to identify the most effective material ratios and processing conditions for sustainable application. The methodology we follow was the next one. First, we start with the raw material preparation. Sargassum SSP was collected from coastal areas, sun-dried to reduce moisture, and milled into fine powder. Sawdust was sourced by a byproduct from industrial wood processing, ensuring low cost and sustainable raw materials. In the experimental design, we implemented two factorial designs. The first varied glycerin and sawdust concentrations to assess the effect of the plasticizer. The second one adjusted the ratio of sawdust to sargassum to determine the optimal biomass composition. To the biopolymer synthesis, the raw materials were combined to cast into molds, then dried under controlled conditions. Several formulations were created by varying biomass and plasticizer ratios to observe their influence on their material properties. Finally, we did the characterization techniques. We measured density, moisture content, water solubility, and water absorption. Thermal stability was analyzed via thermogravimetric analysis (TGA). Structural properties were assessed using X-ray diffraction (XRD), while the surface morphology was observed under scanning electron microscopy with energy dispersive spectroscopy (SEM-EDS). Finally, biodegradability was tested under controlled conditions. For the results, we find that the formulation liked S4A1 with a sargassum to sawdust ratio of 2:1 demonstrated the best overall performance. Its physical properties were a density of 1.94 grams per milliliter that indicates a compact structure. The moisture content was 10.4%, reflecting moderate water retention. The water solubility was of 17.47%, offering a balance between durability and biodegradability. Structural and thermal analysis: the ACM revealed a heterogeneous, irregular surface, suggesting a strong bonding between the biopolymer matrix and fillers. XRD indicated partial crystallinity, while TGA confirmed good thermal stability, suitable for non-structural uses where moderate heat resistance is needed. In conclusion, our findings confirm that a biopolymer made from sargassum SSP and sawdust has significant potential as an eco-friendly material. It combines durability, biodegradability, and thermal stability, making it suitable for application in packaging, agricultural films, and suitable in construction products. Beyond its technical properties, this work demonstrates how two common waste materials can be transformed into viable resources, contributing to environmental protection and the advance of circular economy models. Thanks for your attention.